So welcome back to the SMU Physics Department Speaker Series for Spring 2021. We're continuing our March series today, and its theme of New Frontiers in Physics. And in a moment, I'll introduce today's speaker, Professor Robert Kehoe. Now, I want to point out again that our March talks are mainly showcasing research that's ongoing in our own department, and the aim is especially to highlight faculty who are interested in attracting students to work with their work, to get involved in their work. We currently have no event scheduled for next Monday. There are a couple of people I'm waiting to hear back from to see if that date would work, but we'll finalize whether or not there's a seminar next Monday in the Friday newsletter this week. And finally, some of the usual reminders. So to our audience on Zoom, if you want to ask a question, just type the word speak in the chat window, and that will indicate you want to speak either during the presentation, maybe to ask a question, or at the end during the Q&A period. And we'll get you called on as soon as we can at the next slide boundary, or at using the chat window as a speaker queue at the end for Q&A. We'll get to you kind of in the order you type the word speak. This event is being recorded on Zoom and simultaneously live streamed and recorded on YouTube. So let me, without further ado, introduce today's speaker. Professor Robert Kehoe has worked both in particle physics and astrophysics, attempting to probe the fundamental structure of nature. He is currently pursuing large galaxy surveys with the Dark Energy Spectroscopic Instrument, or DESi, to reveal the impact of dark energy over the last 10 to 11 billion years, just a little bit of cosmic time. He also seeks to measure cosmic expansion in the local universe through the supernova survey of the robotic optical transient search experiment, or ROTSE. His previous contributions in particle physics to the discovery and measurement of the top quark and the Higgs boson with the D0 and Atlas detectors respectively, targeted the mechanism of electroweak symmetry breaking and the generation of fundamental particle mass. Professor Kehoe received a BA in physics from Earlham College and a PhD in particle physics from Notre Dame. His postdoctoral work was in gamma ray bursts and top quark measurement at the University of Michigan and Michigan State University. So welcome, Professor Kehoe. Go ahead, you can get started whenever you like.
Okay, thanks a lot, Steve. So yeah, I wanted to talk about some of the work we've been doing looking at cosmic distances and the geometry of the universe. So cosmic distance is something you'll hear me say more than one time. It's sort of the continuous thread through the different efforts that we're working on. And this slide is actually not just a placeholder. So the two things that you see on this slide are stars and galaxies, and both of those come into play in measuring cosmic distances. And what's more, you may notice just under the O of, there's a little smudge. That is a satellite galaxy of the larger galaxy in the middle of the frame, and there is probably a dark matter halo there, and so those galaxies are populating that. And so that also is part of what we look at to measure cosmic distances, and I'll cover that as I go. But let me start with really the beginning. In my view, the beginning of cosmology, which actually starts with stellar astrophysics. And it starts with a type of star called a Cepheid variable star. And a Cepheid variable star is a star that literally pulsates, as shown here on the left. Let's see if my So these stars actually expand and contract periodically, and it turns out that they have a range of periods depending on their physical characteristics. And something that was very important about them that was discovered over 100 years ago by Henrietta Leavitt is that these stars have their absolute intrinsic luminosity is directly relatable to their period. This is really important in astrophysics and cosmology because measuring distances in astronomy is really, really hard. It's very easy to see things angularly across the sky, but to measure how far away they are is quite difficult. And that also gets complicated by the fact that the physics of those things is not like the physics that we have here at home. So this, by knowing how bright something truly is, one is able to basically know how far away that Cepheid variable star is by looking how bright it appears to be. So this was a critical finding. And in fact, it was used about 10 years later by Edwin Hubble to measure the expansion of the universe. So this plot here is just showing the recessional velocity of galaxies where Cepheid variable stars were identified in the galaxy versus the distance. And you see this nice linear relation. Now, Hubble's plot was not nearly so pretty. And in fact, he was a factor of 7 off. And that's a whole other thing. But the fact is that we get a very nice velocity versus distance profile. The slope of this line is telling us something about what's happening to the universe. In particular, what it's telling us is that the universe is expanding, essentially homologously. And so if we were to think at any point, like take our sun, the universe is expanding more and more rapidly the further out you get. And this is sort of, you may have seen such an example before, but if you took, for instance, raisin bread and you looked at the velocity field of raisins that were near a central raisin versus raisins further away, you would find that the further away raisins would recede from the central raisin more faster as the bread is rising than the nearby raisins. And so that's kind of visually what we think is happening in terms of the velocities of objects. This means the universe is expanding. And what's amazing about this is simultaneously to Henrietta Leavitt's research, Albert Einstein was coming up with general relativity. And this is another ingredient that plays in what I'll be talking about for the rest of the hour. So in general relativity, of course, we have the situation in which gravity is essentially a manifestation of the shape of space-time, and mass tells space how to curve, and space tells matter how to move. And that matter also goes to energy, so light also moves along geodesics in that space-time. And so that was something that Einstein came up with right around the same time as Leavitt. But at the time, he noticed something about his equations, which was that it would cause the universe to contract or expand, but contract if there's a bunch of mass in the universe. And he consulted with his buddies, and they indicated to him that the universe is static. And so this is one sort of standard general relativity equation. I'm not going to go into the theory of general relativity much here, but it's just expressing the scaled acceleration in terms of what we would normally call gravitational physics that includes the mass density of the universe, but also a term that he added, which is we call the cosmological constant, which essentially counteracts the first term. And in the case of Einstein, it kept the universe from collapsing. It could hold it static if you just picked lambda just right. Now, once Hubble came out with his results, he decided that was a big mistake. And for the most part, lambda was dead until 20 some years ago. But I'll come back to that. And lambda is a key point to think about when we think about dark energy. And it also is very important to understand it in the case of the geometry of the universe. And so what do we mean by the geometry of the universe? Well, in this term, probably should have said this before in this equation, we basically have two pieces. We have the contribution of matter and the contribution of dark energy. And so we can look at the total density of each of those terms, matter and cosmological constant. And because energy, of course, is matter, we can write down this expression and divide the conditions of the universe into three different cases. If omega is greater than 1, then that means that the universe is closed. There's more than enough mass energy to close off the universe's expansion. If omega is less than 1, then there's not enough energy in the universe. It may actually diverge outward if it actually has more energy and propulsively pushes it outward. But if it's just 1, then we'll get what's known as a flat universe. And we want to know which one of these situations we're in. That's really a key question we want to answer in cosmology. Which one of these three are we in? Now, there are some indications from elsewhere, inflationary theory in combination with cosmic microwave background, that it would be the flat universe, but we need to measure this. We need to establish this. So now that's kind of cosmology for a long time. But then in the 1990s, people decided, you know, Cepheids are great for measuring distances. However, they kind of crap out at a certain distance. You can't see a Cepheid, you know, millions of parsecs away, but you can see supernovae. And there is a type of supernova that, on paper at least, involves a red giant and a white dwarf that physicists were reasonably confident would have this constant brightness, kind of like the Cepheid, but for different reasons. And it's basically because the white dwarf is a quantum mechanically degenerate object. And as you pile energy through accretion onto this object, it will eventually reach a mass that the Pauli exclusion principle can no longer sustain. And the white dwarf will collapse and explode. Okay, so this is a little video of what that might look like. But you know, this would be a situation that, one, the red giant expands beyond its gravitational reach, its Roche lobe. Some energy will trail into an accretion disk around the dwarf, and then when you hit that 1.4 solar mass limit, it explodes. Okay. What's nice about that is that they always explode at the same mass, theoretically. And so you should get the same explosion every time. Now, nature is never going to be simple, but using that idea and some corrections, two different groups were able to look at the distance. It's a distance modulus, but it's basically the distance versus redshift. If the universe were just continuously decelerating its expansion according to gravity, then this dark blue line is what one would see if you extrapolate from current. This is the nearby universe. What was observed is distant supernovae were above this. They were further away than you expected. And this is the residuals of this plot, so you can see more clearly here. Clearly, these points are not clustered around the blue line. And so, you know, there are different models here, but you can fit this to try to obtain what you would get, and you get that the universe is on the order of 32% matter and 68% dark energy, some repulsive force. And it's quite close to a omega equaling 1. So that's very interesting. And that leads to the question, you know, so fine, the universe expanded, it started to decelerate, now it's expanding again. We're somewhere here. What's it going to do? As it expands, are we going to get enough energy to turn around and start to contract? Is it going to expand and become a flat universe, or is it just going to sort of rip itself apart by accelerating over and over? And again, we have other reason to believe that it may be flat, but we want to measure this and look at the history of the universe to see what's going to happen. And the measurements of the supernovae, you can sort of show them in terms of omega lambda versus omega matter. And what you see is the supernova measurements and the microwave background measurements are quite complementary in terms of the constraints that they provide. And so if you combine this data, then you get this nice little circular area, which looks like it does overlap flat, but that circular area is not infinitesimally small. So we want to really nail that down. And we could do that with supernovae, like I just described, getting better measurements, or we could do that possibly with other means, and we'll go through that sequentially. And I won't bother with that actually. Now, one of the things that has come up, though, is that as measurements have gotten better, and so, in the era originally, let's say 15 years ago, the supernova measurements had quite large error bars, and the prior microwave platform, WMAP, had decent sized error bars, but there was not an obvious discrepancy. But about 8 years ago, and Planck went up, the measurements started to shake out such they're consistently distinct. And we're now to the point where if you take the Planck measurements, which are microwave background measurements, you get, and this number may be a little bit out of date, but you get about 67 kilometers per second per megaparsec, whereas the supernovae give you 74. And that discrepancy is now over 4 standard deviations. So that's a pretty major discrepancy. And that tells you that something is not being accounted for. It could be in one or the other. I'm going to focus on attacking the red thread here in the next few slides. So we're going to do that using the 2 telescopes shown here. And I apologize for the graininess of the photo, but this is our robot, our little satellite on the ground in West Texas, ROTSE-IIIb. And then this is the sort of behemoth telescope, the Hubble telescope, which we use to get spectra. So this telescope robotically observes the sky and patrols local galaxy clusters to look for supernovae. If we detect something interesting, we then request a spectrum from the Hubble telescope. And so that we use both of that information to look at those supernovae. There's other things that one can do as well in that patrolling data, because you can look at variable stars. And this precedes my work on the supernovae. In 2006, I started a group with the undergraduates, the variable stars program, to look at Cepheids. It's taken a while. That was a while ago. But we're now actually getting to the point where we're able to look at constraining Cepheids, or at least testing them. So let's talk a little bit more about Cepheids. Why are they important? Well, as I mentioned, that supernova measurement was done because it was getting to a higher distance scale than the Cepheids could. And that's great. However, Type 1a supernovae, that method does not give you an absolute calibration of supernova. You have to anchor it to the known distance from another source. So Type 1a supernovae are commonly calibrated using Cepheids. So any uncertainty in the Cepheids can impact the supernova 1a measurement. Now, Cepheids are not a stable star. They've left the stage where they're burning hydrogen, and they're maybe moving towards getting to be a red giant, or they may be coming back. And so what's shown on this plot, this is the main sequence, which is basically hydrogen burning stars. This is the luminosity, and this is the temperature. So this is the standard plot we often look at in astrophysics. When a star runs out of hydrogen, they start to evolve, usually cooler, and they'll get more luminous because they're getting larger. And they will pass through this strip here. This strip is really astrophysically interesting because over a very wide range of stellar types, even going down to white dwarfs down here, this strip is unstable. The star does not achieve thermodynamic equilibrium completely. And so they will start to overshoot and undershoot a stable point, and that's where the pulsations come from. The important point here is that the star evolves over time along these contours. These are stellar evolution model calculations. And so you see that stars will move across and then move back and forth. So the classical Cepheids you see sweep through here twice. And then these are also Cepheids, a little different type. And they sweep through the instability strip 3 times before they ultimately go supernova or shed a planetary nebula. And so these Cepheids go through here, and it's a transitional phase. How long do they stay? Well, more recent calculations are that a Cepheid might stay in the instability strip as little as 100,000 years. Well, why is that important? We don't have 100,000 years of data, so how are we going to see this transition? Well, the way that we're going to see this transition is, yeah, we don't have 100,000 years of data, but we do have 10. Actually, we have 15. If we could measure the period of those Cepheids accurately, where accurately is 1 part in a million, if we can measure it accurately over a 10-year period, we could see evidence of this transition and therefore test this model, this aspect of Cepheids. So this is actually a result showing over about 7 years. MJD is just days from 7 years earlier. And this is a residual. So the average period was calculated to be about 1/7 or 1/6 of a day, so 0.15 days to several decimal places. But what's on the vertical axis here is the difference of measurements at different points over this 7 years with their error bars. And the scale here is this number is 4 × 10⁻⁷ days, which is about 400ths of a second. And so a lot of work from undergraduates to clean up data, understand data quality and whatnot, they have gotten to the point where actually over this period of time, all of these measurements are within their errors of that mean, and it looks like a normal statistical distribution. And there's no evidence of variation. This is a test star, and right now the emphasis is on test stars, but the idea is once this work is done, to then apply this to Cepheids. So by that, we hope to test Cepheids and thereby that piece of the supernova puzzle. Another area is we can go to the supernovae of type 1a directly. So one of the things nice about having your own robotic telescope is that you can observe however you like. And we have our telescope patrolling clusters very frequently. So we frequently have the earliest data, even if we didn't get to process it effectively to find the supernova. So the supernova in 2012 CG, if you're interested, this is the early time. What's shown on the x-axis here is days before peak magnitude. All right, so peak magnitude would have been another 8 days to the right. So the data points that you want to look at are, these are models, these dashed lines of how the evolution should happen if you had just the supernova itself. And then there are models of, this is a 2-object situation, so as the supernova explodes, it also does damage to the companion. And that should produce an excess of luminosity at early times. And you can look at how this luminosity varies, sort of bumps up at early times to see whether or not it's consistent with your model. So if it was a red giant, you'd see a large bump. If it was a blue giant, it would be a little lower. If it was a white dwarf, you wouldn't see a bump almost at all at these times. And now the best way to do this would be to look into UV. And so there is some Swift satellite data here, and it is above, but there's only 1 point. There's another telescope that has a B band magnitude that seems to be a little high. But then we have the ROTSE data there, and we run it open filtered, which means we actually get a little bit of ultraviolet light in there. And it's actually higher than the B band magnitude at a time when there really wouldn't be any visible or red flux. So this seems, taken all into account, not just with the ROTSE data, seems to indicate the best fit was to actually a blue giant companion. So this is an area where, maybe our red giant white dwarf model isn't quite right. There are other results, not by us, but by other people, that seem to suggest that there are type 1As that are white dwarf events. And they would not have a Chandrasekhar mass limit. So the jury's a little bit out on exactly what's going on with the 1As. So one should be a little careful and do tests to make sure that those results stand up. What we're doing is to go to a completely different type of supernova, which is a core collapse supernova. So this is probably what you typically think of when you think of a supernova. You have a giant star, it's got a lot of layers because it burned its hydrogen, then it burned its helium, et cetera, and it looks like a big onion. And what happens is for really massive stars, they develop an iron core, and iron is a real problem because you can't get energy out of fusing hydrogen with anything. And so this star, as it's building up its layers, so let's say it's a 25 solar mass star, the first layer, that takes 7 million years, using up your hydrogen to make helium. Then to go from helium to carbon, it's 700,000 years. So that's a lot faster. When you burn your carbon to oxygen, that's only 600 years, which is a blink. To go to a silicon, it takes 6 months, and then silicon into iron takes 1 day. So every one of these stages, you get hotter and you have higher and higher rates of reaction, and you just blow through this material in the fusion process. Once you get that iron core, you're stuck, and then the core will collapse because you can't get any energy out of it in a fraction of a second, right? We've actually seen this happen once. In a salt mine underneath the Lake Erie, actually not far from where I grew up, and in another mine in Japan, the Kamioka mine, 18 neutrino events were observed. They were spread out over 10 seconds, but neutrinos do have a tiny mass, and it's very consistent with this picture of a fraction of a second core collapse. But of course, it would be nice to have another event like that with a lot more neutrinos. So that's the core collapse idea. And now a lot of core collapse supernovae have what's called a hydrogen envelope in their outside. And so when the supernova finally explodes, and this is a video of about 200 days of a supernova measurements from the ROTSE-IIIb, and you can see the supernova sort of in the center here. During the time that it's bright there, it's in what's called the recombination phase, or the plateau. And this is a time when the supernova is too dense for the light to completely get out, so it ionizes, and then that re-radiates, and then finally the light gets out. And this goes on for a while until the star expands enough that it becomes transparent, at which you see the light drop off suddenly. And this is the light curve that goes with that. During this recombination phase, it turns out that this is a fairly simple physical system. You don't have to know much about the science of what caused the supernova, as long as you understand that this is a thermal object that is expanding rapidly. And so you can get rid of a lot of that underlying astrophysics to try to do that. Now, the problem with these supernovae is that they're not as bright as type 1As, which is why a lot of people don't use them as much. However, they have completely different systematics that govern them. So in any case, so what we use is something called the expanding photosphere method. So imagine that you have a black body, and it's at some temperature, and that black body is expanding homologously. And as it's expanding, it takes up a certain amount of area, but it's at a given temperature. And from your point of view, you see that area, and given the black body spectrum, you should be able to calculate what flux you get for that, modulo a couple corrections like extinction, okay? So if this star has some angular size to you, then it has some total area times the flux from the black body, and you can then calculate what the flux would be. Imagine that you know the size of the object theta, then the time at the value of time that you will have to get to that theta equals the distance to that object times theta over the velocity of the ejecta that's going to produce that angular size, plus whatever your initial time was. T0 you measure. V phot is the photospheric velocity. You get that from the spectra. The temperature, you can get that either from photometry or the spectroscopy. And then you measure the total flux. We use the ROTSE telescope as a bolometer. With all of that said, what you don't know is, well, there's theta. These two give you theta, once you have theta, you know what time you're looking at a given observation, you can use all of this to figure out what D is. So it's a very nice method that uses more basic physics that's a little less scrupulous. That it's not quite so obvious because this term here is the dilution, and there is some astrophysics here that's still that's not been as well figured out, I would say, as it needs to be. But by and large, this is a very different way of going about it. And so in order to do this, you need to have for every observation a knowledge of what the temperature is doing. You don't have enough measurements from spectroscopy or broadband photometry to get that. So you have to model it based on what you have. So what we've done is taken several external supernovae, looked at their time, their temperature behavior, put them on a common footing, and then we use that for our supernovae where we have 1, 2, 3, or 4 anchor points, and we figure out an average model so that we can then calculate the temperature at every epoch that we have observations in our light curve. And we do that for velocity and we do that for temperature, but these are the temperature plots. With that, we can run those equations and we can calculate what the distances, we can calculate the distances as this is basically the phase, and here's theta, so this is the time. And so according to the equation that I showed you, the slope will give you the distance. And you see all of the different measurements for the 12 different supernovae there. And they all line nicely on a line. They don't diverge badly. And so those slopes are where you're getting the distances. This is a little too blurry to read the distances, but they're given there on the slides. And from that, we then, since we know the recessional velocity from the spectra, we can then make our Hubble plot. So we have the distance versus the velocity, and it's only 12 supernovae, but in actuality, so what's shown here is 2 samples. One is a local sample, which has a very large effect from peculiar velocities. There's a low Z sample, which doesn't. And so the 3 different curves are just each of them separately and then they combine, but they seem to be quite consistent with each other. And so these are the measurements that we get. These errors are just statistical. We're still working on the final systematics, although Ryan Staten showed a preliminary version of these in August. And so right now we're down to about 4.8 kilometers per second for megaparsecs just from these 12 supernovae. So that's another way in which we're trying to look at new techniques to try to test the measurements of dark energy. All of that is to pursue what's called the cosmic distance ladder using what are called standard or standardizable candles. If I have a Cepheid or a supernova at a given distance, and I know how far away, I know how bright it truly is, and I know how bright it appears, I can figure out its distance. What we're going to switch now to is we're going to do another one which measures cosmic distances by using a standard ruler. So we're going to use something that is a fixed size that is not going to change over time, and we're going to watch how big this thing appears at different times in the universe to watch the universe expand. And we're going to do that by looking at large-scale structure in the universe. So what you have here in these 3 panels are the distributions of matter in the universe at early times. And then over time, where there's a little bit of an overdensity, matter attracts matter and you get more of a clustering. And that will just continue more and more. So where you had more of an overdensity, you tend to get very high dense regions. And where you didn't, you get voids. And so this ends up giving you large scale structure in your galaxies, okay? The way that this starts is from, it basically starts from what happens in the time before the cosmic microwave background is liberated. So what I'm going to show you here is a video with 4 components: dark matter, gas, photon, and neutrinos. Gas is baryons. Dark matter is not interacting except weakly. Photons interact electromagnetically and neutrinos barely interact. They interact weakly. So what you're going to see is that in the beginning, neutrinos are going to decouple from gas, baryons, very quickly as they move out because they're not interacting. But photons are going to stay very closely connected with gas until we get to 300 some thousand years. And then they're also going to be liberated. And then the final thing that you will see is there will be, where the gas is a little bit congregating, it will pull dark matter and dark matter will pull gas. And so they'll both tend to start to look like each other at a characteristic distance scale. So you can see here, neutrinos have moved away, but you've got photons and gas are the same. And now the photons have decoupled. There's a big difference between where the dark matter and baryons are, except now over time, the baryons now start to attract the dark matter and vice versa. This distance is something you can figure out. It's mostly laboratory physics to figure out that distance. And that becomes the ruler that we're going to care about. So this is a one-dimensional plot, but of course, this would be happening in 3 dimensions. And so that frontier would basically be spherical around that original dark matter location. And it's this scale, this distance, that is going to be our standard ruler, okay? How do we measure that? Well, the way that we measure it is we have to be able to see something that tells us where the mass is. And we can't see the dark matter, so we have to use galaxies. They're the only thing that's bright enough, consistently enough, that we can find at very, very large distances. And so what we do is some version of measure a point-to-point correlation between galaxies in pairs to figure out what the typical distance scales are. And so that video that I showed you will leave you with something that looks like this, where you'll have some sort of falling distribution in general. But if there's a BAO, if there's that feature, then you will get a bump here. And this scale, which is called the BAO feature, or distance scale, is something that we know to be about 150 megaparsecs, but usually when we do it, it's going to be 105. There's a few other effects in there. So we want to measure this distance, but we want to measure this distance in different redshifts and see the universe change over time, okay? The way we're going to do that is with the Dark Energy Spectroscopic Instrument, which is at Kitt Peak. It was an existing 4-meter telescope, but we ripped out the optical assembly here and the focal plane and a bunch of stuff at the bottom. And we're putting in there basically a bunch of fibers, optical fibers, so that we can run them to a spectrograph and get spectra. And the idea is to do a survey of 3-dimensional survey. So a lot of surveys like Dark Energy Survey or LSST, of the Vera Rubin telescope, or even CMB, those are angular correlations. There's not any depth. But by having a spectrum, one can measure the third coordinate through the redshift to very high precision. And this is very useful because it gives us a way to constrain cosmology in that direction. Well, hopefully I'll get to it. The survey itself will cover as much, well, pretty much all of the non-dusty sky that we could observe from the location. So it's almost all of the North Galactic Cap area and a good chunk of the south. We avoid the Milky Way galaxy, of course. There are 4 target types that go from low redshift to high redshift for Lyman alpha quasars. The emission line galaxies are particularly important because they cover the region where it appears the universe went from a decelerating to an accelerating universe, but we don't know that for sure yet. So we really want to measure that well. And we want to measure our cosmological parameters really well. So for instance, this is the precision error on the distance scale, which will tell us what we need to know in many cases. And DESi is shown here in black. The existing BOSS results, which are the prior stage 3 survey, are shown there. So DESi clearly does much better there, covers a fuller range of redshifts. and does quite well in comparison to Euclid and W-FIRST, which is now the Nancy Grace Roman Space Telescope, and covers a much larger redshift range. Over 5 years, we're going to gather 32 million spectra and over 14,000 square degrees to do this survey. So that's a huge. Now, how do you do that? Well, in the prior BOSS case, the way that they did this is to get the fibers on the galaxy locations, they had to machine a plate where the coordinates of the galaxy should land in the focal plane. And they have a whole bunch of plates for different regions they want to look at. They have to take the plate out, and then they have to plug in the fibers, every single fiber, and they got to know which one they plugged in where, so they know what spectrum is what at the spectrograph end. And when they're done with that, they can get, in their case, 1,500 spectra. But you can imagine this is a fairly painful process, and they didn't want to do that. So what we're doing is the whole area is instrumented in the focal plane with 5,000 robots. And those robots each have a fiber positioner that can rotate in a small region. So this is what you can see here. And this is one sector called a petal in the focal plane, and it's partially instrumented. And you can see these things are tracing out a little disk area. Okay, that's not relevant, but I hope you saw that. And so by doing that, we can find every location in the focal plane by telling each one of these positioners where to go. All right. Sorry. Yeah, they basically have 2 degrees of freedom in theta and phi to get there. Uh-oh. Hold on.
No problem. I think we just lost your desktop share.
Yeah, that's
a really impressive robotic system.
okay.
I've never actually seen that video before.
It's really cool. There's 5,000 robots crammed into the focal plane behind, and then there's all their electronics is right behind it. It's very cool. Okay, so can you see my screen?
Yes, it's sharing again.
Can you see my screen?
Yes.
Okay, good. So this is just a one positioner, so you can see maybe a little better how it's moving. Okay, so it's got those 2 different degrees of freedom. So I won't spend a lot of time because there's more that I want to talk about. So one of the things that's really exciting, I haven't talked about DESi in a long time, but we're running. So in fact, we've been taking James has been taking remote shifts downstairs in the room 15 control room as data's been coming in. I think he just got done with another shift this last weekend. And so, we're running and we're taking data. This is currently survey validation. So this might be called commissioning in a particle physics experiment. But basically, we're taking science quality data now. We're done with commissioning, but we're still working out the kinks in various systems. But this is actually showing some of the online software, looking at all of the petals. This is online spectroscopic reduction that we've been involved with developing over the years. This is one spectrum at a redshift of about 1.38. And it might not look all that impressive, but the important part is this is an emission line galaxy, and this is an O2 doublet. And so when you blow it up, you get a very nice O2 doublet. It's a forbidden transition. That's the key marker of this type. So with that doublet alone, we can usually identify emission line galaxies with very high efficiency and low background. But there are other lines that we look for as well. I wish I could show you more. There's another one I would show you. Here's a quasar at a redshift of 2.59. And you get very nice Lyman alpha, and you get some other features in here. This is a histogram of what we've got. This is not even up to date, but you see we've now got 120,000 bright galaxies at low redshift, tens of thousands of luminous red galaxies and emission line galaxies, and about 10,000 quasars. Now, as a reference, this is 60,000 emission line galaxies. We're supposed to get 18 million. So we're really barely scratching the surface, but it's still a lot of galaxies and a lot to look at. And then this, the red curve is kind of looks a little crazy, but from the very earliest data pre-COVID shutdown, this is an efficiency plot. Actually, Ryan made this, Ryan Staten, and it's showing that we should, for emission line galaxies, get efficiencies of approximately 80%, and we're in that ballpark. But that's very early days. Now, I don't have data to show you in terms of cosmology, so I just wanted to introduce very briefly the kinds of studies that we're getting involved in and that are important for these measurements. One is that you have to account for the fact that your observations impact your measurements. So we have the situation where, yeah, we saw galaxies, but we need to know exactly what the probability that we would have seen that galaxy, its efficiency, its redshift efficiency, given the telescope, the data reduction, and the redshift fitting. The reason is because that this histogram, which is the 2-point correlation function, it's a number density. And so I need to know that I know this number really well. Otherwise, I could sculpt the shape of this distribution in a way that would bias where I fit the peak, this BAO peak, and then that can impact my cosmology. And since we're trying to get to fraction of a percent on DESi, this is a very important thing to do. And it can come in because of seeing, meaning blurriness, how bright the moon is, air mass, different effects. And so that's one thing that's being studied. And one of the ways to do that is by looking at this property and varying those conditions and seeing what happens. Another thing that's very important is, as I said, galaxies are not dark matter, and they're subject to a number of physics effects that dark matter is not, and it's not very easily calculable. You could do hydrodynamic calculations, but you can't do them to the volumes that you need to do this cosmology. So that physics has to be encompassed somewhere. It's not fundamentally different to what you would get in a particle experiment when you're thinking about jets, where you don't, from first principles, calculate the jets. You have sort of a phenomenological model that you parameterize. So there are different levels of doing this in terms of the galaxy to halo connection. And one of the ways is to figure out how to put galaxies into halos using a physical model that's tuned on data. So that's something that we're starting to work on. And so here you got, for instance, the number of galaxies versus the mass of a halo. And what's shown is the number density in terms of central galaxies and halos and satellites, and they have different properties, and you fit those and you try to make sure that they make some sense. Okay, so those are things that are ongoing, but it's extremely early days, and a lot of work needs to be done to have anything that will be usable on the data. But we're hoping to be able to get some science even out of the survey validation period. The projected sensitivity of DESi, this is the sort of looking at the scale of the universe relative to time. And so, now is here. So if you run back the clock, the supernovae are the blue points here. And so you see this thing flattening out here because of, going from decelerating to accelerating. And then zooming in on this, you can see the blue points are the last two supernova points. DESi will be here blowing up this region. And these different lines, these different colored lines, are different equation of state parameters that are over plus or minus 3%. So that gives you an idea of how well we would be able to probe that. And of course, we have several measurements at these redshifts. So that's one thing. Another thing is to look at the Hubble parameter. As I said, DESi, because we get that third coordinate, we can directly measure the Hubble parameter. And we can do it at every redshift bin we choose. So from a redshift of 0 out to 3.5, we can get redshift measurements. And in fact, we're actually expecting most of these measurements to be less than 1% in each redshift bin. So right now, the measurements are, a whole survey's got one measurement and the error bars are sort of plus or minus 5, more than 5%. And we can't really tell what's going on. But the goal is to measure this whole contour and figure out exactly what is going on in there. And that's what we're thinking is happening, roughly in the last 10 billion years. Now, these are not the measurements. They won't be so nice and neat on this point. And this is just a model, the standard lambda CDM, but it's to sort of give you an idea of how the sensitivity of the measurements would look when we have the data for the full survey. I think we started 5 minutes late, Steve.
Well, the introductions take 3 minutes.
Okay, all right. So I'll give this, and then if people want questions, I have a couple other slides. So in summary, hopefully I didn't go too fast through that. We've looked at how stellar transients can be very useful to cosmology, and they're still very much part of the argument that's going on. There's a few different ways to come at them, both within the supernova and stellar transient sample, either looking at the underlying Cepheids, looking at the type 1As and testing them, or coming up with alternative supernova types and with different systematic uncertainties. But then we've also talked about how we can also use galaxies and very, very different physics to look at the way that the universe is expanding over time. And that gives us these really very precise measurements compared to what existed before. What's shown here is what we would expect omega lambda versus omega matter to be. And so weak lensing, this would be coming most likely from the Vera Rubin telescope, would give you an oval something like this, and DESi would give you an oval shown in red. And if you took the two of them together, you get a pretty narrow constraint on both of those very important parameters. So we've built a sports car, and I think we're really looking forward to taking it for a drive over the next few years and seeing what it can do. I'll leave it with that. There is a whole bunch of other science I didn't talk about, and I've got a couple plots on that. So if you want to, I'll leave that slide up, but that's kind of what we're doing.
Okay, sorry, I was waiting until this huge lightning strike that just happened out here stopped echoing before I unmuted, but thank you very much, Bob. Let me try to give you a little bit of applause here rather than thunder. Right? So, okay, so we'll go ahead and open things up to Q&A now. If you want to, oh great, Pavel, you're up first, and let me find you, and you should be good to unmute. Oh, Pavel, you're having that strange high pitch thing again. Whatever you did the last time fixed it.
Okay, so now you should hear me.
Yes, perfect.
Well, Bob, thank you so much for the very detailed review of the DESi program. You mentioned the 0.4 sigma discrepancy of the different kinds of measurements on the Hubble constant. What are the prospects for resolving it? So what exactly can reconcile these issues? And the other question that I have is that there are alternative explanations for certain effects that you see, like, for example, there is a paper by Subir Sarkar saying that maybe there is no dark energy at all. So what do you think about it?
Yeah, so I think, well, one has to entertain that possibility. I'm agnostic as to whether there is or is not dark energy per se. And if we find on DESi there's no evidence of dark energy, then so be it. Obviously, if we take a number of different measurements and we come up with a consistent result, even if they're numerically discrepant, then there's something going on. But I think it's still probably too early to say that. In terms of answering the question that you mentioned, I think there's a number of things. I mean, each of the methodologies need to be looked at in detail to find out where their weak points are. So I've given you a smattering of an idea of how you might do that in at least a couple ways with the supernovae. There's a lot of other ways that you can do it as well for all of the methods, as far as I am concerned. But I mean, the BAO measurement, if you hear a lot of the people that are in favor of that would say, well, you don't need any astrophysics at all, except that's not really true, because you need to compensate for the fact that galaxies do not land exactly where the dark matter does. And so that's physics that you have to deal with. Now, those systematics may be small, but I think we need to see, I think it'll be very telling to see the next round of supernova measurements, for instance, from the Dark Energy Survey, versus the next round of BAO measurements from the galaxy surveys, which are very different. LSST has a whole program on supernova measurements of type 1A and type 2. So I think, you know, those things have to be pursued. And, you know, I think if you asked me, I think the supernovae type 1A is probably good enough to find dark energy. I'm not sure that I'm as happy with it in terms of to nail down exactly what it is, because you have to rely on the star itself. And whereas I think the core collapse supernovae, I think, is a more clean way to go. And the BAO approach is also very clean. But, you know, that's an argument that you have to have. And I think it's going to take, I don't think you could just say, well, I don't believe the Cepheids. There's been a hell of a lot of work that went into those as well. And, but they all have to be compared against each other. And sometimes these things disappear. I mean, I remember my time on the Tevatron, there were several times there were discrepancies supposedly between CDF and D0 or whatever, and they eventually went away. So.
Thank you.
Yeah.
Okay, are there additional comments or questions for Bob? While we're waiting for people to type speak in the chat window, I actually had a question for you, Bob, if you don't mind. And it's actually on that slide right there, 35. Okay. So can you just help me to understand the behavior of these, what look like error bars? I'm assuming that the lines on the red points are supposed to be some kind of uncertainty. The uncertainty appears to be small, then it grows, and then it shrinks again at some point, and then it grows again. What's going on there in this?
Okay, very good question. So first of all, let me explain this plot first. This plot is existing measurements from BAO of prior surveys. This is a supernova measurement. So you'll notice the BAO is consistently below the supernova. It's not very statistically significant, but this is the kind of thing we want to see. When you get a plot like this to compare to that supernova measurement, that will be very telling. Now, why does this look the way it does? These points are modeling this black line. So the cosmology is that black line, and you're assuming that you measure the value. But then the error bar is an estimate of what the total statistical plus systematic error bar will be in that redshift bin. Why does it flare out and things? In this region, you have below 0.5, you have the bright galaxy survey. So there's not a lot of galaxies here. And as you get volume, more and more volume, you get more and more galaxies. So you get smaller error bars. Okay. This region is the emission line, the luminous red galaxies. So you get a lot of galaxies here. This region is the emission line galaxies, which go up to 1.6. But then once you get to 1.6, you have to rely on quasars, and you don't have a lot of quasars. So this region is a little bit lower statistics because there's just not a lot of quasars out there for you to pick. You have to be able to target them. This region is dominated by Lyman alpha forest, and there's not a lot of quasars out there, but the Lyman alpha forest works. Let me see, hold on a second here. So the Lyman alpha forest works like this. Lyman alpha, it's just the Lyman alpha line, but it could be an emission line, but it could be an absorption line. And in this region below where the quasar is, you have a bunch of Lyman alpha absorption features. Those absorption features correspond to the redshifts where other mass is between the quasar and you. So the Lyman alpha forest actually allows you to probe the clustering at all of the distances between you and the quasar itself. So you get a lot of power out of this small sample. So that's why this is large here, and then pretty small everywhere else.
Okay, that makes a lot of sense. Thank you. I see Joel has a question. Okay, Joel, you should be good to unmute.
Yeah, thanks, Bob. On your summary slide, actually, sorry, it was the slide after your summary slide, where you had this list of things. This is probably a super detailed question, but I noticed you had the effective number of neutrinos, an error
Yes.
bar there. Could you just comment on where that comes from?
So,
Or more specifically, what forecast, like to what forecast are you referring to?
so actually I have a plot there. So basically what happens is, let me go back to the number. So there's two numbers here. There's the sum of the neutrino masses. So that's actually the number that you hear mostly people on DESi are trying to figure out. My recollection is that this number comes out of the same analysis, but I haven't followed that as much detail. So, but what happens is, to the extent that neutrinos have mass, they essentially blur out the BAO feature, and the impact of that causes you to have a constraint on neutrino mass. So by fitting the BAO feature, you can get that. So by doing that analysis, now for some of these analyses, you have to use Planck, because Planck CMB initializes BAO. We have to know what the scale was to be able to get to follow it through. So what you see here is neutrino mass versus dark energy, lambda, and omega lambda. And so red here is Planck plus DESi, okay, BAO measurement. And green is Planck plus Vera Rubin using their weak lensing measurement. And you see that they have different sensitivity. One is a little more sensitive to dark energy, one is a little more sensitive to neutrino mass. But then if you take the product of them, you can get this oval. The number that I quoted, the 0.017 electron volts, is coming though from the width of the red. All right, so I can't tell you in detail the analysis the way it's done, but that's the measurement that's being done.
And Joel, if you want to follow up with that, you should be able to unmute.
Okay. Yeah. Thanks. Okay. Thanks, Bob. Yeah, I was interested in the N effective measurement, but that's okay. I think I might know the paper. Is it the Font Ribera paper with the forecast table?
I'd have to. I don't remember. It's been a little while. I'm glad that you're asking about that, though. Let me dig it up and I'll send it to you.
Okay. Thanks. I appreciate it.
Yeah, I haven't. Even though I'm mostly a particle physicist still, I haven't really been paying attention to the neutrino as much. And but obviously we have neutrino physics going on in our department, so I wanted to put it on here.
Thanks.
And you just talked about it this at noon, so I'll send that to you.
Okay, great. Any additional comments or questions? Going once, going twice. Okay, well, Bob, that was great. Thank you very much. To the students within earshot, either on the live stream or on Zoom, if you have questions, don't be afraid to contact the speaker directly, especially if you're thinking about research over the summer or long term. And that'll be true, of course, for all the faculty speakers we've had from our department in December and in March. Without further ado, I think we'll thank the speaker one more time, and we'll go ahead and close the event out. So thank you, Bob.
Should I send you a hard copy? I don't know. Are you posting?
Yeah. Whenever people can share slides with us, we make them available on the seminar calendar. Okay.
All right. I'll send that. Yeah.
Okay, great. All right. Well, thanks, everybody. Have a good evening. Thanks for coming.
Well,